So let me recall. As before, H is L2 of R, which we are identifying with the Fock space of Cn. Huh? You want to talk about relative trace? We will have an occasion. We will talk about the characteristic function of the relative trace of a state. So at that time, I will recall it again. Okay. So then we had the following. We defined the map. Rho is a state on H. Then we define rho hat of any alpha. Alpha is in Cn. Rho hat of alpha equal to trace of rho W of alpha. Okay. Then this rho going to rho hat is a bijection. Bijection between these two sets. It's not writing. Yeah, it'll just come. Oh, yeah, it stopped sharing. Yeah. I need to share it again. I don't know what's the problem. Probably with the internet connection. It has come now. So you tell me when it's not writing. This is better. Last time when I was connecting the iPad, it was not writing there, but the screen was there. Now it will be clear if it's not. So states on H2 between these two things, between and the function. So maybe I will write it here. All those functions from Cn to C satisfying f of 0 equals 1, f is continuous, and the function k alpha beta equal to e power I imaginary part of alpha beta, f of beta minus alpha is positive definite. So we proved these things. Definite. Okay. We proved these things. So to talk about a state, it's enough to talk about the characteristic function. Okay, let me type like this. So let's see how this characteristic functions behave with respect to some transformations, some mappings of state. Okay. So examples. I mean, these are not examples of state. We will get to examples of state, but before that, we'll do this. Examples. So if U is a unitary in Cn, these are unitaries. Then we have defined this gamma of U. I'm just recalling for the
They're connected to some other Wi-Fi. No, the iPad.
No. No, there is a EDU-RAM. Usually the Wi-Fi, there is no Wi-Fi in the classroom, but I can see very mild EDU-RAM is there. So it's connecting to that, I think. No, I don't think so. It's not getting connected. I don't see it. I don't know. If it disturbs like this, it will be a problem in the class. Then we have defined this gamma of U, E of alpha equal to E of U alpha for alpha in Cn. Okay. Then this is defined on the total set of vectors. Then gamma U extends as a unitary. We know this extends to a unitary. Okay.
Sorry.
No, no
I thought
problem.
it was 5:15, so I was.
No, that day your class was there till 4:30
Yeah, yeah,
for
so
some
5 is
reason.
the right time.
Yeah, 5 is the right time. So I decided to have it at 5:15 because
Yeah.
5 is the right time.
Sure.
That's no problem. So anyway, I haven't done anything. I have just recalled what we have done in the characteristic function. There is a characteristic function gives a bijection between states on H and all functions satisfying those conditions, which we have already seen. So this is the first example. This is not example. This is how characteristic functions behave with respect to behave with respect to some transformations. So if you have a unitary, maybe I will recall it again. If you have a unitary in Cn, if a unitary matrix in Cn, okay, then we can define, this was done in the last course. I'm recalling it again. Then define gamma of u acting on E alpha equals gamma E of U alpha for alpha in Cn. So these are exponential vectors. If you have a unitary in the ground Hilbert space UCn, then gamma of u is defined on the Fock space or L2 of R. Gamma of u acting on E alpha is E of U alpha. Then we can see that this is easy to see. Then gamma of u acting on E alpha, gamma of u acting on E beta equals E times gamma u. I mean, it is just gamma of u alpha. I mean, by definition, it is just gamma of u alpha u beta, gamma of, I mean, E of, which is equal to E of u alpha, E of u beta. Okay. And that is equal to exponential, the function exponential u alpha u beta. And that is equal to exponential alpha beta, this inner product. And this is equal to E of alpha, E of beta. Okay, because the exponential vector satisfies that inner product condition, because of this, it will follow this. So this is defined on total set of vectors. Exponential vectors are a total set of vectors. And total set of vectors, this gamma u preserves the inner product. So you can extend to the whole L2 of it. So this implies gamma of u. This is what is called second quantization. Of u. Okay. U is defined in the ground Hilbert space, and you have a second quantization. Gamma of u extends to unitary. Extends to a unitary operator on L2 of R or gamma of Cn, whatever, L2 of Rn. Okay. So did I write L2 of R there? I sometimes tend to write L2 of R. See, L2 of Rn. It should be L2 of Rn. Okay. Okay. So this is the second quantization, gamma of u. Now we want to see the example 1. So if a rho is a state, this is direct verification, state on H. Then you can conjugate it. You conjugate the rho with, rho is an operator, just a trace class operator. You can conjugate with any unitary and get a new state. Okay, but then we don't have any information about the unitary. That unitary can be anything. So if we have a u is in some unitary in Cn, then we can define a new state, which is gamma u rho gamma u star, which is equal to gamma of u star, of course. Gamma of u whole star is gamma of u star, which you can verify. Okay, so this is a new state. Okay, this is also a trace class operator. If you multiply trace class operator with any operator, it's again a trace class operator. And since they are unitary, you can take this gamma. This will have the same trace as rho, because you can take the gamma of u on that side inside the trace, and gamma of u star, gamma of u will be 1. So this is a state. Okay, it's easy to verify. I don't want to write all that. Okay, it's easy to verify this is a state. And this hat of this is equal to this hat at alpha. This characteristic function of this new state at alpha is going to be rho hat at u star alpha. Okay. That is clear. Let's write the proof. We want to compute this gamma of u rho gamma of u star at alpha, hat at alpha, the characteristic function of the new state at alpha, which is nothing but trace of, I should have said it here. This gamma of u satisfies this property. Okay. This satisfies this property. Further, This was easy to verify. We proved it last time. Now gamma of u, W of alpha, gamma of u star. Further, it is also true that gamma of u1, u2 equal to gamma of u1. Maybe we will need it later. Gamma of u2, gamma of u star is equal to gamma of u whole star. And this is equal to W of u alpha. Okay. We verified all these things last semester. Gamma satisfies this condition. I mean, it's a nice representation. It's just a representation of the unitary group on the Fock space. You have unitary group on the Cn, then you can ground Hilbert space, you can represent it on the Fock space. This is why it's called second quantization. The first quantization is U itself. Okay, that is the first quantization. It is just, I mean, U has a physical meaning. You quantize it as an operator, as far as I understand. That's what. Okay. This is what first quantization of unit. U is related to some evaluation of system or something. It's just a. I mean, this is a mathematical object. This has some meaning in physics. So you quantize it. This is a quantization. U is a quantization. But the same U can be represented on the Fock space, which is called second quantization. It comes from physics. I'm not too sure. Because the second time you are representing on a different Hilbert space. So whatever the physical object you are representing on this Fock space. So I think that's why it's called second quantization. Okay. That's my understanding. So. Okay. So, and it satisfies all the properties of the unitaries, okay? And it also intertwines the Weyl operator here. That's a nice thing, okay? So, because of that, this is equal to trace of gamma of u, the gamma of u rho, gamma of u star, W of beta, sorry, here I should have, no, W of alpha, sorry, alpha. W of alpha. So, this is the characteristic function evaluated at alpha, but this is equal to rho gamma of u star, W of alpha, gamma of u. Eh?
Okay, now
It didn't come.
Yeah.
Okay. There is a lag. So this is equal to, of course, trace of rho W of u star alpha, right? Now this is equal to rho hat of u star alpha. That's all. Direct verification. Okay. So by conjugating with gamma u, you get a new state, and that state is nothing but evaluated at rho hat of u star alpha. Okay. That's all. Okay. This is something about. That's all. I think it's clear. We'll go to next example. Now we have more unitaries. We have Weyl operators. They are also unitary. So how it will behave with conjugating with Weyl operators? So that's the next question. So next proposition or example. Example 2. Oh, it's completely gone. Is my laptop is connecting to something? I mean, iPad is connecting to something. No, it is CMA. It's connected to CMA only. There is no video room. I don't see any other network. I don't know why. Okay. So now rho is a state, some state on that. Rho is a state as before. State on H. And you have a alpha. Huh? It's not appearing again. Maybe I should connect it through some. No, it's not mirroring.
Sharing is cost. So cost here on the map.
No, here I have to do something. It's not screen mirroring. There is some screen mirroring here. It's not happening. Okay, I will share it again. Nothing else to do. This will take a lot of time unnecessarily. Again, oh, it's showing something else. Sorry. This is the one.
By sharing it via the cable,
Hmm?
you have a.
Yeah, the cable, will it work?
No, it's okay. I mean, the cable also should.
Okay. But internet is too fast. All this wireless is too fast. It's very near and I don't know, some other technical problem. I mean, when other things are functioning well, this is maybe a problem. Okay. So we have an alpha in Cn. Okay. Now we have a state on H, alpha in Cn. Okay. Then we can conjugate our state with W of alpha also. Okay. Rho W of alpha star. Of course, W of alpha star is W of minus alpha. So this is a new state. This at beta equal to e power, it should be plus, I think, imaginary part. Anyway, we'll do the calculation, it will be clear. 2 and rho hat of beta. Okay. Proof verification, it's just verification. Okay. So we want to, so we have the following: W of alpha, W of beta, W of alpha star, which is equal to minus alpha, W of alpha star, equal to, so e power minus 2i, right? Minus 2i imaginary part of alpha beta times W of beta. Okay, this is the Weyl relation. Okay, you will get one imaginary part when you have, I mean, for the W of alpha plus beta, if you apply it twice, you will get this. Okay. So because of this, now we want to talk about W of alpha, rho W of alpha star, hat at beta is nothing but the trace of W of alpha, rho W of alpha star, W of beta, it's gone.
Yeah, maybe try the cable.
Yeah. So now this is, of course, you use the trace property, you can bring this W of alpha to the other side, rho. W of alpha star, W of beta, W of alpha. So we have this W of alpha on the other side. So that is why, I mean, here, here you have minus here in this, here you have minus here, the 2i minus you have. So you, because you have W of alpha star, you will get plus here. Right. So that is equal to trace of, so this, that's a scalar, e power 2i imaginary part of alpha beta only, and then rho W of beta. So which is what we want, which is equal to e power 2i imaginary part of alpha beta, and which is just rho hat of alpha, rho hat of beta. Okay, that's done. Okay. So when you conjugate with W of alpha, you get this. So now we get the first example of Gaussian states. So when you conjugate with Weyl operators, you get this number and then rho hat of this. So let's first take the first example.
Yes, I tried with the cable. Stop share.
How do you tap
Stop.
stop share? How do you do the cable?
And then share it.
Hmm.
The via cable. The second.
Okay. Hello, this computer is synced with Rhino. What is this? What should I do?
We'll just move the, yeah.
Hmm? Oh, something has to be inserted. Okay, so we have found how when you, I mean, when you conjugate with the second quantization and when you conjugate with the Weyl operator, how the state transforms, that we have seen. So first example is example 1, or example, again example, the vacuum state. So you take, suppose if rho is this, E of 0, then we have already seen it in the last semester. I'm just recalling it again. When rho is this, then you want to compute the rho hat. Then rho hat at alpha equal to, so trace of W of alpha, this E0, E of 0, E of 0, W of alpha, just trace this. So which is going to be W of alpha, E0, W of alpha E0, right? Yeah. So which is e power minus alpha square by 2. Okay. Then everything else go away. I mean, there is nothing. Inner product between alpha and 0 is 0. And e power alpha will come. E power alpha, the inner product between e power alpha and e power 0 is also 0. Right? W of alpha acting on e of 0 is e power e alpha. If you want, I write it. Okay. This is just e power 0 into e of alpha. Right? W of alpha acting on E0 is e power minus alpha square by 2 times e alpha. So because of that, you get this. And that is 1 anyway. So that inner product is 1. So this is just e power minus alpha square by 2. So rho hat alpha is this. Okay. And if you fix a t, I mean, this is the characteristic function we have found. I will anyway come to that. I mean, we will talk about what is a Gaussian. We will define formally what is a Gaussian state. And then we will see that if you insert a t alpha, fix an alpha and insert a t, then this will be the characteristic function of the usual normal Gaussian. So incidentally, I want to ask something. So you want for presentation, I give you 2 choices now. If you really want, otherwise I will do it. Okay. One is proving the classical Bochner theorem. See, since this course we have done all basics. Maybe we'll do the classical Bochner theorem and compute the characteristic function of a classical Gaussian, multivariate Gaussian. It's not very difficult. It's just 2 pages, 2-3 pages. Okay. Either you can present that, one of you. The other one is Stone-Von theorem. It's just an exercise in KRP's book. Okay. And he sketches the proof also. It's not very difficult. You have to give the argument. I mean, since it's an exercise, we will anyway discuss it. You can come to my room sometime, we will discuss it. Okay. So you can present one, you can choose that. Or if you don't like classical probability, I will do it one class and you tell me later. Okay. It's up to you. Okay. But it's because we are going to do this, it's better to know.
I think I do the stone one.
So you will do the Stone-Von theorem. So okay, he opted first. So you will take it, you will do the Bochner's theorem or something. Okay. Okay. So then it will be clear that this is the characteristic function of a normal Gaussian when you have a t there. Okay. So that will be clear from that. Okay. Okay. So there is some, so now we know some other vectors we know is exponential alpha itself. Okay. So, but then that's not a unit vector, right? It has norm e power minus alpha square by 2. So the next example is you define what is called chi alpha. Chi alpha equal to e power minus alpha square by 2 of e of alpha. Okay. Because e of alpha has norm e power minus e power alpha square by 2. Okay, you have to multiply by e power minus alpha square by 2. Okay, and to make it unit vector. So then this is notice that this is nothing but W of alpha acting on E0. Right? Okay. Then chi alpha, I mean, you can directly do the calculation with this. I mean, do the compute the trace, which is just some inner product, or you can use the theorem which we have already proved, chi alpha, which is nothing but W of alpha is 0. Okay, W of alpha is 0. This outer product, whatever this outer product or rank 1 operator, and this is nothing but W of alpha, this F0, W of alpha star. You can write down the definition, you will get that this is true. Okay, just apply it on some vector, you will get that. Okay, so now this is, so now this implies, these things implies this chi alpha, this is our rho. Okay, rho equal to this. Okay, suppose we have rho equal to this, then rho hat equal to rho hat of beta, okay, equal to, of course, this is our definition of beta equal to, because this is just the conjugation by the Weyl operator. So this is just going to be exponential, the plus, no, there we got plus, right? So 2y alpha beta, imaginary part of alpha beta, okay, times the characteristic function of chi0. I mean, chi0 is E0, okay? You see the hat at beta. So which is going to be exponential. I'm writing it as like this, minus beta square by 2 minus plus 2y into imaginary part of alpha and beta. If you want, you can write it as minus 2y imaginary part of beta alpha. Okay, if you want. Because if you conjugate the inner product, the imaginary part will become minus. You can write it like that. Then you will see that this is a, I mean, this is also Gaussian, but the mean is not 0. Earlier it was standard Gaussian. Okay, here the mean is not 0. Okay? The variance is minus beta square. No, variance is 1. Variance is 1, still 1. It's at beta, no? Variance is, no. If you are, I mean, what I mean is, I'm saying what I mean doesn't make sense. What I mean is the following. If you have E of rho hat of T beta, that's what you have to consider. Okay. And suppose then this is going to be exponential minus T square norm beta square by 2. Okay. Minus 2y T times imaginary part of alpha beta. Okay. These are all constant. This imaginary part of alpha beta, everything is constant. So this, that whatever the constant that is coming there, that will be the mean. And this beta square by 2 will be the variance. Okay. So this we will see later. Okay. So when we define formally, for the time being, this is the quantum characteristic function. We will do some classical theory and get back to this, define Gaussian state formally, and then we will talk about all these things. So what we have got is, say, but if you allow beta to be R2n, beta is in Cn, right? Cn is like R2n. Okay. So this is somehow resembles a multivariate Gaussian in R2n. Okay. But not every possible Gaussian in R2n will be, you will be able to get here, because there is, I mean, the positive definite condition, there is an exponential e power I imaginary part something. That will create some problem. And that will, so see, R2n is Rn direct sum Rn. Okay. So you can, for anything in Rn, okay, you have something. So this is something like you want to have, so you want to have something in the real line, P of alpha plus I beta, where alpha and beta comes from Rn. Okay. If you have P of alpha, then that gives some, that is some Gaussian random. I mean, you under this, that will be some Gaussian, some random variable. P of I beta is some random variable, but there is some uncertainty principle. There is a restriction due to uncertainty principle. So all possible multivariate Gaussian state on R2n will not be possible. There will be some restriction. Okay, in the way. But for the time being, if you look at it, this is the R2n. If you, I mean, this resembles R2n Gaussian multivariate random variable with identity is the covariance matrix of that, and mean is given by some vector in R2n. That imaginary part of alpha beta. See, this imaginary part of alpha beta can be written as some real inner products of some alpha prime beta, which is possible to write like that. It's possible to write. It's just, I mean, imaginary part is, you are just, I mean, if you have some imaginary part of two vectors, alpha 1 plus alpha A alpha 2 and beta 1 plus I beta 2. What will be the imaginary part? This will be the, you take the inner product between these two and you take the minus of the inner product between these two. That will be given by the inner product between the actual alpha or something and some other vector in the real Hilbert space. I mean, in the real part of that, right? See, if you have an inner product on a Hilbert space, on any Hilbert space, you take the real part of that, that will convert it to a real Hilbert space. Okay. So Cn can be, you can Cn as an inner product. The inner as a vector space, R2n and Cn are same. But if we consider the in Cn, the real inner product, that will be like Rn. That is Rn. So why I'm saying is the reason, I mean, the reason we are talking about this is this resembles the characteristic function of a Gaussian multivariate Gaussian random variable with covariance matrix identity, and the mean is given by some other vector in Rn. That vector is this alpha prime. That vector is this alpha prime which satisfies that condition. It resembles that. Okay. 2n, R2n. So alpha prime is an R2n. R2n. But then, so we got a multivariate. It's like we got the multivariate multivariate Gaussian measure on R2n. We got something corresponding to that in this quantum generalization. But we will not be able to get everything. We got it with the identity. See, if you take the vacuum state, that is a standard one. That is with mean zero and what is that? Mean zero and identity is the covariance matrix. So here also the identity is the covariance matrix, but the mean can be anything in Rn. So by doing something, you will get all the vectors in Rn as mean. So mean is not a problem. So the question is, we have almost got identity covariance matrix and all vectors as mean. That we have got. But whether we will be able to get all covariance matrix in R2n, so that will not be possible. That is because of the uncertainty. That's what we will see later. Okay. But to get other things, we need something more. Before discussing that, that we have to see, we want to get examples of more Gaussian states. For that, we need to talk about something called symplectic automorphism, symplectic isomorphism of this Fock space. Okay. So before going to that, symplectic isomorphism of Cn. Okay. That is just linear map which does not preserve the inner, need not preserve the inner product, but it will preserve the imaginary part of the inner product. I will define it.
So also, here there's like I is there in the equation.
Correct.
So like
No, characteristic function is a complex valued function. I will be always there.
No, but like when you see it in R2n, are you taking like only one half of it or something, or are you just?
No. This I is the function. See, R2n, if you take any characteristic function in the real case, it's a function from the probability space to complex number.
Yeah.
So it's a complex valued function. I is there.
Okay, you're not seeing it like a element in. Okay, yeah, thanks, sir.
This is just a value in complex number. It's not in Cn or something. Okay. This I is in, this is just a complex number, not in Cn or something. A characteristic function is always a complex valued function. Okay. That is this I. This I comes in the real case also.
So I was like you're seeing like C as R2.
That is for this alpha and beta. The alpha and beta are in Cn. Okay. So we, if we to the analog, we want to check. Analog we want to compare is with R2n. Because we have something in the imaginary part, real part also. Okay. Okay. So before going to, so this is with the covariance matrix identity. We want to see what are all the possible covariance matrix of a Gaussian state. That's what we want to see. So we want to move to that next. That is our next aim. So before that, I will just tell you how it behaves with tensor product and relative trace, and then we will start doing that. Okay. So the first one, this is example again. So if rho 1 is a state on L2 of Rn1, okay, and rho 2 is a state on L2 of Rn2, okay. Then you have rho 1 tensor rho 2. It is rho 1 tensor rho 2 is a state on the tensor product of these two things, right? It's a tensor product and is a state on L2 of Rn1 tensor L2 of Rn2, which is actually equal to L2 of Rn1 direct sum Rn2, right? Okay. Is it clear? It's not clear. It's because of the Fox-Space property. Exactly. This is gamma of Cn1. This is gamma of Cn2, which is same as gamma of Cn1 direction Cn2, which is same as Rn1 direction Rn2. Okay. We are using that. Okay. So we can have whichever the picture you want to use. See why we are using L2. It will be clear when we start talking symplectic isomorphism. Okay. I mean, till now it's not clear because we are more or less using the facility of the Fox-Space only, Fox-Space picture. Okay, certain things are not possible in the Fox-Space picture. We have to come to L2. Okay? So that's why. Okay, now row 1 tensor row 2 hat. Row 1 tensor row 2 hat of alpha direct sum beta. Okay, where alpha is in C and 1, beta is in C and 2, right? Then this is going to be row 1 tensor row 2 is going to be row 1 of hat of alpha times row 2 hat of, as you expect. This is clear. Okay. And should I write it? I mean, okay, there is something you need to remember. I mean, we have already seen this. So if you have two Hilbert space, so this is digression fact. You have already seen this. If we have two Hilbert space H1 and H2, two Hilbert space, then the Fox space of H1 direct sum H2 is isomorphic to gamma of H1 tensor gamma of H2. The map is you take E of X direct sum Y to E of X tensor E of Y. So E of X direct sum Y is total in H1 direct sum H2. I mean, gamma of H1 direct sum H2. That is clear because that gives all the element. And E of X is total in gamma of X1, H1. E of Y is total in gamma of H2. And if you have a total set, you take the corresponding tensor, that will be total in the tensor product. That also we have gone through. Okay. Because of all this reason, I mean, this is Hilbert space, you have to work with totality and all that. Yeah, that is total. That also we have seen. So because of all this theorem put together, this is the isomorphism. Okay. So this is the isomorphism. Now verify this. So, I mean, this is just an exercise for you to verify. Convince yourself. There is really nothing to. So if you call this map as what is the what do you want to call? I want to call it as a big W. Okay. This small w is a while operator. Big. Yeah, that is also used. There are many. So that's what many things are used here. One is the one is, I mean, exponential vectors are total. Then if we have a total tensor, total set will be total in the tensor product. And another thing is this this map is defined on the total set, which you can extend, which preserves the inner product, so it can be extended. I mean, it has to preserve the inner product. That's extended. So we use all that. And another thing to verify is this under this W, if you call this unitary as W, okay, which we will forget this unitary, okay. Most of the time we will not refer to this unitary. We will always treat the gamma, the Fox space of H1 direct sum H2 as Fox space of H1 tensor Fox space of H2. We will always treat it under this identification. But for the time being, if you have the W, then W, this big W of X tensor Y, X direct sum Y, W star equal to W of X tensor W of Y. Okay. You just verify that this property is satisfied on the exponential vectors. You write it on the exponential vectors, but you need to verify at least once. I mean, okay, I will tell you what to do. So, okay, let's verify this. Okay, no problem. See, you want to verify what is this W of X direct sum Y, this acting on E of some other X1 direct sum, maybe alpha direct sum beta. Huh? It's clear, no? So I don't need to verify. You take, I mean, it's just all the norm, everything breaks out. See, you have the norm inner product on the on the top of E, okay, inside the exponential function, which will be product. See, if you take the inner product of direct sum, that will be sum of the inner product or sum of the norms. Sum of the norm square, not norm. Sum of the norm square or sum of the inner product. okay, which is inside the exponential, which will be product. So you will write it as a product. So it will be, I mean, if you verify the inner, it will be clear. Okay. So you just verify this verify this identity on exponential vectors, and that is clear. Okay. So that's right. So because of this, it's just clear. Now it's clear. The property of the tensor product of the state is clear. That's what we want to verify. So so you want to verify what is that? Now rho 1 tensor rho 2 hat of alpha direction beta. Okay. I mean, which is element in Cn1 direction Cn2. Okay. Which is equal to trace of rho 1 tensor rho 2. Okay. Times W of alpha direction beta, right? Which is same as we are assuming it's same as rho 1 tensor rho 2, W of alpha tensor W of beta. Okay. Now trace respects the multiplication. This is just trace of rho 1 W of alpha times trace of rho 2 W of beta. Okay. That's all. Which is just rho 1 hat of alpha, rho 2 hat of beta. Okay. It's just direct verification. There is really nothing. Okay. Okay, now we will talk about relative trace. So under relative trace, this is another example. Okay, if rho is a state on H1 tensor H2. I mean, maybe I will call it as L2 of R11 tensor L2 of Rn2. Okay. Okay. Now you want to find the relative trace. What is relative trace? You want me to recall what is relative trace? It is a, see, if you have some state, if you have some operator, so recall. If T is an operator in B of H1, tensor B of H2, which is same as, I mean, if you want, this is B of H1, whether I write it outside or inside doesn't matter. I mean, it will be the same thing, because this space can be written as linear combination of the elementary tensor and take the corresponding closure in the topology. Take the linear combination and take the corresponding closure in the topology. The same thing works for the operator also. Okay. So that's why you can write it as B of H1 tensor H2 or B of H1. So B of H1 tensor H2 is same as B of H1 tensor B of H2. Okay. Same thing. Okay. B of H1 tensor H2. Okay. T is here. Then, I mean, T is trace class and trace T is finite. Okay. So, see, if you have an operator on a Hilbert space, if you have an orthonormal basis, then you can write an operator as an infinite matrix. Not every infinite matrix will give you an operator. Okay. But if you have an operator, you can write it as an infinite matrix. You just have to take the partial, I mean, the matrix unit, T, E, I mean, T, EI, T, E, J, whatever. You just have to take this. Okay. That will be the matrix elements, right? The trace is nothing but the sum of the diagonal element. TEI is just, it's like the usual trace here. Okay. So T1 tensor T2, if you have, I mean, this is an exercise I asked you to verify. I'm just telling you, this is an assignment for you to verify that. Okay. So I don't want to recall the whole thing. What I'm saying is, if you have one EI is an orthonormal basis for H1 and Fj is an orthonormal basis for H2, okay, then you will have EI tensor Fj. This is an orthonormal basis for the tensor product, okay, H1 tensor H2. Now you will have an orthonormal basis indexed by Ij prime, right? You will have a, I mean, matrix indexed by Ij prime, okay. Now you want an operator on H1, okay, on H1. Just you have an operator T on H1 tensor H2. Now you want to get an operator on H1. I mean, for us, that relative trace is defined by that property. Trace of X tensor 1. I mean, we have defined, we had a property, no? This satisfies this property. Trace of X tensor 1 times some T right? No, what was the,
Is equal to trace in the first Hilbert space of X2.
yeah, which is just same as T1x. So this T1 is the relative. This is a property, then I mean, this is a abstract way of saying it. Then I am going to define an operator that will give an operator, it will satisfy that. That's what I want you to.
Partial.
Yeah.
Partial trace is called relative trace in
Oh.
mathematics. That's this is partial trace in quantum computation physics. So this is a relative trace. And I mean, this is also what is called, you can call it as conditional expectation also. This is actually satisfies something called
Isn't it marginal?
marginal. No, from algebras, we will define, that is an algebra. B of H1 tensor H2 is an algebra. B of H1 is a sub-algebra, which sits at B of H1. So from a big algebra to small algebra, you can marginal, I mean, that is what is marginal is for state, no?
Yeah.
This is conditional expectation is from algebra to algebra. So this is conditional expectation also. Okay. All these things will be related if you consider the corresponding. Okay. Then you have to consider state as a linear functional and all that again. Okay. So it satisfies this property. How you get this operator T1 is you take T, okay, T has this I, J, this thing, right? I prime, J prime. Okay. Now you define T1 of I prime equal to T of summation over J, okay, T of Ij, comma, I prime J, right? You just sum it over the J, Ij, I prime J, right? Correct, no?
Yeah, I think it's.
You are just I prime. This gives that this gives an operator on that. If you specify this, okay? But this is only scalars. You are just getting the numbers, right? That numbers are given by that. So it is not clear that that will give an operator. But this thing will satisfy that. So I mean, it's clear. I mean, using that theorem, you get an operator. That operator has this coefficient. If you prove that, then it is clear, right? You prove T1 is a bounded operator. You get a bounded operator T1. And the T1 has this property. You know what is T1 I prime, which is just the T1 evaluated at the corresponding orthonormal basis. E I prime using that. That will be equal to this. Okay. Further, it is also true that, I mean, this I gave it as an assignment. I want you to get convinced. Okay. I was just telling you. So trace of T1 will be equal to trace of that original T. Okay. That's all. So I erase all these things. Now the theorem, whatever I'm going to state, this will be direct. It's clear. It will be clear. So you want to write? Are you writing? Okay. So now if you have a state on the tensor product, then we can define the relative trace or partial trace, whatever. Then rho 1 equal to trace 2, which would call it as trace 2. Okay. Trace 2 of rho. Okay. Then rho 1 hat of alpha is nothing but rho hat of alpha direct from 0. That's all. Just add 0 to that. Okay. I mean, it should be clear. The proof should be clear. Rho 1 hat of alpha, which is nothing but trace of rho 1 of W of alpha, right? By the theory, by the property we have mentioned, this is equal to trace of rho of W of alpha tensor 1, right? Right? Which is same as trace of rho W of alpha direct from 0. So which is just rho hat of alpha direct from 0. It's direct. Okay, so now we know how it behaves with respect to tensor product, how it behaves with respect to the relative trace or partial trace. Just partial trace, just the restriction. We just have to add 0 to the other. Okay. Okay. So if you have written, I will start something new. Okay. So which is very important for Fock spaces. I mean, In the Fock space theory, the actual, see the isomorphism of the Weyl representation. So what is Weyl representation? Okay, so this is what I want to call it as new topic. So shall I start? So there is this, you would have heard this name symplectic in many places, symplectic geometry, symplectic. So symplectic means it preserves the imaginary part of the inner product. I don't know in many other places how, what is that. For us, the symplectic isomorphism is the following. Okay. So what is the Weyl representation? Weyl representation satisfies the following: W of alpha, W of beta equal to e power I imaginary part of alpha beta times W of alpha plus beta. Okay. Now, if you have a map on the Cn, so this is for alpha beta in Cn, or you can take it in any Hilbert space. I mean, we have Fock space for any Hilbert space. You can have for any Hilbert space. Okay. Okay, for Cn, for the time being, we work with the finite representation. Okay. Now, if you apply something on this, I mean, we want to have a, see this and it's also true that W of alpha in Cn, you take the span and closure in the strong topology. Okay, it generates in the strong topology B of gamma of Cn or L2 of Rn, whatever, gamma of Cn. That's also we know. Okay. So if we define a map in Cn, okay, which represents, I mean, which gives, I mean, which is the same, whether it is the same representation of what I want to say is, if you have an S is an operator from Cn to Cn, okay, then consider this alpha going to W of S alpha. When will it give the same representation as when will it give the same representation of, I mean, when will it give the same Weyl representation? So if S alpha, imaginary part of S alpha, S beta equal to imaginary part of alpha beta, okay, then you get the same representation, right? Then W of S alpha, W of S beta. I mean, this is how the product behaves, it says, okay, e power I, imaginary part of S alpha, S beta you will get, which is same as I alpha beta, okay, W of S alpha plus S beta. Okay. So it is like you have, see, you have the same B of H, okay, in this you have this, contain this W of alpha in Cn, okay, and same B of H, you have W of S alpha, okay, and you take the algebra generated by this, ordinary, no closure, just algebra generated by this, algebra generated by this, S alpha. This is some algebra, this is some algebra. And this W of alpha going to W of S alpha is a homomorphism. It's a homomorphism because it satisfies the product condition. Because it preserves the imaginary part of the inner product, it will be a homomorphism. The question is whether that homomorphism extends to the whole of B of H. Right? When, I mean, will it extend is a question. Yes is the answer. Okay. It's clear, no? I mean, it's clear why I say it's a homomorphism. Homomorphism means it has to preserve the product. If it has to preserve the product, then that's a scalar. Homomorphism is also, algebraic homomorphism is also a linear map. So scalar should come out. Scalar should come out as e power I, imaginary part of alpha beta, which should be same as imaginary part of S alpha, S beta. I mean, it will be a homomorphism if and only if S preserves the imaginary part of the inner product. Okay? If it satisfies the S.
This is a homomorphism or the map alpha to WS alpha.
W alpha to WS alpha. That's a map. Yeah, that is a homomorphism.
Okay.
That's an algebraic homomorphism. This is the algebra generated. You take the algebra. I'm just taking the algebra. You see. W of alpha going to W of S alpha. This is a homomorphism between the algebra generated by W of alpha, right? Alpha in, which is just the span, okay, Cn, to the algebra generated by W of S alpha. Okay, alpha and Cn. Okay. Both these sets are generate the B of H. So does it really extend to the B of H? Does it give a automorphism of B of H? In general, it's not. When H is infinite dimensional, it's not the case. And not H is infinite dimensional. When if you replace Cn with the infinite dimensional Hilbert space, it will not be true. It need not be even W of S alpha need not even generate the whole of. I mean, it can be very weird. It can generate need not the algebra generated need not look like B of H. There is something. Yeah, still, yeah, correct. Okay. So here, if we have an invertible operator, it's okay. Let's assume S is also invertible. I will define it. Okay. So the question is the following. Okay. So let me make the definition. Okay. S from Cn to Cn is invertible. We need not worry about it's Cn, so we need not worry about continuity. But if it is infinite dimensional, you have to say it's continuous and inverse is also continuous. Okay. Invertible. It's a linear map. It's a real linear map. Okay. It's real. Let me write it. It's not complex linear. It's only real linear. Okay. So S is Cn to Cn. You can consider Cn as R2n if you want. Okay. But since we are going to introduce the imaginary part of the inner product, we need Cn only. We cannot escape it. It's actually it's a map, it's a linear map between R2n to R2n. It's a real linear map. Real linear map. Okay. And invertible. Such that S of alpha, S of beta, they need not, but imaginary part equal to imaginary part of alpha beta. It's an invertible real linear map which preserves the imaginary part of the inner product. Of course, a unitary will define. Unitary is complex linear, so it's also real linear. Unitary is invertible. It preserves the inner product, so it will preserve the imaginary part of the inner product also. Okay, that's not quite clear, but you can check. I mean, if it preserves the actual inner product, it will preserve the real part, it will preserve the imaginary part also. Okay. You can verify it. Okay. You just have to convince yourself about that. Okay. It's true. Okay. So unitaries will satisfy. This is what is called a symplectic isomorphism. Isomorphism of Cn. Okay. So now if we have a symplectic isomorphism, so this is also called spin group or something. Okay. S is all symplectic isomorphism. It's also called. This is actually map in R2n. So it will be, I mean, there is a different definition. It's also called SP2n, I think.
Real, linear, invertible.
And preserves the inner product.
Two inner product spaces that preserve the
imaginary part. Yeah. Imaginary part of the inner product. That's called symplectic isomorphism between them. The Hilbert space is complex. You can replace Cn with any complex Hilbert space.
What is the
no, it is the Weyl representation we have. Physics.
Like any canonical example that is not.
Yeah, we'll see a canonical example. Unitary is one example. Non-unitary example we will immediately see after this. Okay. So.
But unitary is more.
Yeah, unitary is unitary. Yeah, but unitary will not be useful for our purpose. We want to get Gaussian state with covariance matrix not equal to identity. Different Gaussian state. We want to, I mean, we want to get all possible Gaussian states. Okay. So how do we don't have an example? Okay, how do we get it? So for that, we have to use this.
Oh.
Okay. We will have a different prescription, but we will use this also. Okay. It will be clear. Okay. So, okay. So I mean, as I said, this gives a algebraic isomorphism between, see now, okay. So now W of alpha and W of S, so W of S alpha satisfies the following properties, of course.
So it's called spin group.
It's called spin group. I think so. There is a, I mean, there is a, this again a big branch, spin group, study its representation and all that. I mean, okay. So this W of S alpha, and I mean W of S alpha, if you consider this, for example, satisfy the same property, W of S alpha plus S beta. I want to write the following. W of S beta equal to e power, since the imaginary part is preserved, this is just alpha beta. W of S alpha plus S beta. Okay. So this implies W of S alpha, okay, alpha in Cn, satisfies the same Weyl relationship. Satisfies Weyl relation. I mean, not with S alpha, with alpha beta, right? It's not working.
So the motivation is to get all quantum concentrates through the.
Yeah. Here. Symplectic isomorphism has different purpose. It has, yeah. Satisfies the Weyl relations. Okay. Okay. So Stone-von Neumann theorem implies the following. There exists, I mean, the point is this. It's also further, this is also true, no? This is irreducible also. W of S alpha, alpha in Cn, okay? This contained in BH is irreducible also. Right? The span closure with respect to strong topology of this is equal to B of X, right? Because S is invertible. Because, I mean, otherwise it's not true. Because S is invertible, to get it's also irreducible. So there is not the in the Stone-von Neumann theorem, there is a tensor product. Small Hilbert space K is there, no? It will not be there. So this implies there is an isomorphism. There exists a unitary, which we call it as gamma S from the Fock space, gamma of Cn to gamma of Cn, such that gamma of S, W of alpha, gamma of S star is equal to W of S alpha, right? This is what Stone-von Neumann theorem says. Okay. But then what is gamma of S? We don't know it explicitly. See, this is a, can we get a single gamma of S so that it gives a representation of the spin group or symplectic isomorphism? That's the question. So in physics, so if you insert there is a gamma of S. Okay, this gamma of S is unique up to scalar. If you insert an alpha of unit modulus, you get an alpha. I mean, instead of gamma of S, if you use alpha times gamma of S, that will also satisfy this, right? You get an alpha, you get an alpha bar, that will cancel and you will get this. Okay. Whether can you choose this gamma S uniquely in a way such that this gives a representation of the spin group on the Fock space. Okay. Actually, this is not still physics literature. They say it's not possible. Okay, but it has been proved that it is possible, but they don't seem to know it. I mean, actually, I proved it, but it's it's in a giant paper with someone. So it's proved in 2005. Even in KRP's paper, he knows that. He knows means he has listened to my talk. But still, he says that in his paper that it's not possible to get this gamma of S as a single representation. Okay, but it is possible. He says it's possible in finite dimension, but then there is a plus or minus one parity is there. He says, but I don't think that's also not there. Okay, so I will tell you how to get this gamma of S in finite dimension. It's true for infinite dimension also, but there will be to get this gamma of S, you need some Hilbert-Smith condition and other thing. Okay. So that's a different theory. So for infinite dimension, we want to get this. So first I will give you an example of the symplectic automorphism, symplectic isomorphism. Okay. Then for that I will give you an assignment. where you will explicitly get this example. Okay. Then I will state the theorem, I will prove that theorem. Okay. So this is an example. So suppose A is an invertible operator, GLNR. This is all invertible operators, invertible matrices if you want, okay. Operators on Rn. Okay. Okay. Corresponding to this A, you define SA from Cn to Cn by SA acting on X plus Iy, where X and Y are in Rn equal to AX plus A star inverse Y is inverse. I mean, the operation inverse and star commute. Okay. I mean, you can take A inverse star is A star inverse, okay, which you can verify with the inner product. I mean, a star is adjoint is something which satisfies the inner product relation. And inverse is something which satisfies the left inverse, right inverse condition. You can verify. I mean, it is unique. It's determined by the property. Okay. And you can see that A star inverse are both will satisfy. I mean, okay, you can verify using that. You can verify that A star inverse is same as A inverse star. Okay. So it doesn't matter which way you write. So given an invertible operator on Rn, so that is GLNR means invertible operator on Rn. Okay. Invertible, it's a n cross n matrix which are invertible. Okay. Then you can define a SA, and the real part it acts as A, imaginary part it acts as A star inverse. Okay. Then you compute the imaginary part. Imaginary part of X plus X1 plus IY1, X2. Factor of? Sure. Yeah, sure. Otherwise, there is no. Okay. So this is equal to inner product of X1, Y2, right? Minus Y1, our is conjugate linear in the first variable, Y1, X2, right? This is the imaginary part of the inner product. On the other hand, if you calculate imaginary part of SA of X1 plus IY1, SA of X2 plus IY2, okay, this is equal to, this will be equal to AX1, okay, AX1, then it will be A star inverse Y2, okay, minus AY1, A star inverse Y1, AY2. I mean, you just write the definition and compute the inner product, you will get this, right? Now, A star inverse, if you bring it as A inverse there, that will get cancelled, and which is equal to original one, X1, Y2 minus Y1. Y1, X1. This is X2, right? X1, Y2, Y1, X2, right? Yeah. Okay. So it preserves the imaginary part of the inner product. Right? A star inverse will come as A inverse here, it will get cancelled. Here, A star inverse will go as A inverse there, and it will get cancelled. So we have lot of, these are all not unitary. These are all not even complex linear. They are not complex linear. It will be complex linear if and only if A is a unitary. If A is a unitary, so this is an exercise you can verify. Okay. If A is a unitary in the real, I mean, A is any invertible operator. If A is unitary in Rn, real linear unitary, okay, then SA, I mean, no, so let me write it. Let me state it as the following. Yeah, GLNR. Okay, then SA is complex linear to start with, if and only if A is a unitary, real unitary. Okay, I mean, it preserves the inner product. By unitary, we mean it preserves the inner product. A is real unitary on Rn. Okay. It will follow. If you write the definition, and it's good exercise. Okay, it will follow immediately. So we got a lot of examples of this. Now the assignment I want to give is the following. Of course, given this A, how to get that gamma of A? That is our aim, no? We want to get gamma of S. Given a symplectic isomorphism, Stone-Van theorem abstractly says that there is a gamma of S, right? Stone-Van theorem says that there exists a gamma of S from gamma between the corresponding Fock space. S is between Cn to Cn. Actually, you can change this S from some, I mean, you can't have invertible operator from Cn to Cm, but if it is infinite dimensional Hilbert space, you can have from H1 to another H2. Okay, provided they are both infinite dimensional. Both separable means separable, non-separable means I mean, it should have the same infinite cardinality. Okay, whatever it means, countable, uncountable, whatever. Then you can define this gamma of S from the different Hilbert space also. Okay. So then then the Stone-Van is not true there. But here the Stone-Van theorem that there is a gamma of S between the corresponding Fock space which satisfies this condition. Okay. Stone-Van says this, but we don't know what is gamma of S. But for this A, SA, given a, we get SA. Given a, an invertible operator, we get an SA which satisfies this thing. SA is also invertible, of course. Clearly, that's also invertible. And that is real linear. It's only real linear. It's not complex linear. And it preserves the imaginary part of the inner product. So we want to, I want to give the right example. I want to give the precise, I want to give the concrete gamma of SA. Okay. Okay. So let's talk about this. So SA in GLN R and SA as before, as above. Okay. Okay. Then define. Shall I say gamma of SA? Okay. Yeah. Gamma of SA. Okay. Acting on a function f at x, okay, equal to determinant of A. A is a invertible matrix, so determinant of A is not equal to 0. So minus half f of A inverse x. For f in, for x in Rn, f in L2 of Rn, right? It takes a function f in L2 of Rn to another function, right? There is nothing. You are just in x, you insert A inverse x. Okay. And you multiply for it to be a unitary, you have a determinant of A. Okay. Then gamma of SA is a unitary. And satisfies. I mean, it looks complicated, but I will tell you it's very easy. Very easy to prove. That's why I'm giving as assignment. Okay. Satisfies gamma of SA, W of alpha, gamma of SA star equal to W of SA alpha. So the map is clear, right? It takes a function in Rn, L2 of Rn, and it gives a new function. Okay. That is just transformed by a matrix. So it will be again L2 if you use the, it's clear that it's a unitary. It preserves the norm is clear. You want to take the L2 norm, you will get an L2 norm here. Just you apply change of variable, you will get the Jacobian, which will be the determinant. The power minus half is because square you want to consider. Okay, so you will get the determinant, the Jacobian which you get out is determinant. Just use the change of variable. So it will be clear from change of variable that it's a unitary, right? It's a unitary is clear. Now, how to verify this property? Okay, for that you have to go through the problem in the end semester exam. The problem says the following. So, this is the end semester exam problem. Refer. End sem.
Unitary matrix.
Exactly. Yeah. That semester. So you have this unitary between gamma of Cn to L2 of Rn. Okay. So use that unitary and see what is the action of W of alpha. You still don't know what is W of alpha and W of I beta. Okay. And use that to verify. W of alpha is defined on exponential vector, right? E of beta. You are just defining it as E of beta as some e power minus alpha. Abstractly, you are defining. Actually, use that to verify that W of alpha on L2 of Rn. Alpha is in Rn. For alpha in Rn, W of alpha acting on a function f for f in L2 of Rn. I mean, alpha comes from Cn, but I'm taking it as an Rn. Okay. Is f of, this at x equal to f of x. I asked you to, I didn't give the answer, no? I asked you to get the answer. So I think it is x minus 2 alpha or alpha, I'm not sure. Okay, you use this. Okay. On the other hand, W of I alpha, I'm using the same alpha, acting on f at x, will be e power I alpha inner product alpha x. This is the real inner product. Okay, of, there is no minus, I think, there's plus. Okay, plus f of x. It is just direct verification. You use the definition when alpha is real, okay, and I alpha is purely imaginary. For this is how the Weyl operator acts. You have the map E alpha. E alpha, you know what is E alpha. You know the definition of W of alpha. Use that definition. It's a function. Terms will come out and it will be clear. It is this. Okay. It will be clear. So you use this map, this thing. Okay. From that, it will be clear that gamma of SA, then use gamma of SA, W of alpha, gamma of SA for alpha real. Alpha in Rn. It will follow that this is equal to W of A alpha. Just use the definition. Similarly, gamma of SA, W of alpha, there's a star, SA star will be W of A star inverse alpha, I alpha. Sorry. Use this definition. It will be exactly, just write down the definition, it will be clear. Okay. That's all. So from that, it follows. And the assignment is not finished yet. I want to tell you something more. Okay. And further, E of 0, gamma of SA of E of 0, okay, equal to, I only want you to verify that it's greater than 0, but it will be equal to, I think it is this, half into determinant of A plus determinant of A inverse power minus half, I think. Okay. This you have to compute. This computer, there is no real computation. You have to use the change of variable, then use the fact that e power minus half x square by 2, this is the Gaussian in that. So if you integrate it over Rn, it will give 1, it will not give 1. So 1, you will have 1 by 2 pi power n by 2, no? Square root 2 pi power n by 2. Equal to 1, right? This is the Gaussian random variable. So then Gaussian density. Okay, standard Gaussian density. So if you take the whole thing, it will be 1. So if you compute this, you will precisely get something like that with the A somewhere. Use change of variable, that value will come out. That determinant something will come out times 1. Okay. It's all direct verification. Okay.
That's greater than 0.
Greater than 0, right? It's a number. It's a positive number. It's supposed to be a complex number, right? Gamma s is a unitary. E of 0 is a unitary. In a number is a vector. E of 0 is a vector. Gamma s is not positive. It's a unitary. So it will be strictly greater than 0. The reason for this condition is With this condition, you can fix the gamma SA up to unitary, up to. You can, I mean, gamma SA, see the A, see.
So like, you had two choices.
No, up to, see, this property, no, this gamma SA, this is satisfied if it is this property, gamma SA, W of alpha, gamma SA star. If it is satisfied by some one unitary, then multiply by a unit modulus, alpha times some unit modulus number. Some Z times gamma SA will also satisfy that. Okay. But if you impose this condition, it will be determined uniquely if you use this condition, right? If you have, you cannot have alpha there. Unit modulus. It will come out as alpha, it cannot be greater than 0. It will be complex number, right? Right? So that alpha has to be 1, right? If you have a Z which is complex, if you multiply gamma SA by Z, if you impose this condition, it has to be 1. It cannot be anything else, right? So that is the theorem I want to prove. The theorem is the following. So there exists a homomorphism, if you want to call homomorphism, from the spin group sp2n or whatever to B of Fock space L2 of Rn or whatever, Bl2 of Rn. Okay. A going to gamma of A. So S going to gamma of S. We reserve A for the positive operator. I mean, this invertible on Rn. Okay. S going to gamma of S. Okay. I mean, it's well defined. It should be well defined. You cannot determine it. I mean, it should be well defined. There should be no alpha. I mean, it's also strongly continuous, but I don't want to prove it. It goes through something. Actually, this map is also strongly continuous, but we don't need it. Okay, so I will not prove that. Okay. So this I will prove next. Satisfying, sorry, I forgot. Satisfying the two conditions. One is gamma of S, W of alpha, gamma of S star equal to W of S alpha. This is one condition. And E of 0, gamma of S, E of 0 is strictly greater than 0. This is a generalization. Oh, I took a lot of time. Okay. Okay. No, this is the generalization of the second quantization of unitaries. If you have a unitary, you can second quantize it. That's what we talked. Okay. That's a very direct way of defining. Okay. As you can see, this gamma S cannot be defined in Cn. We don't know the definition. I mean, it becomes very complicated in gamma of C in the Fock space picture. There is no, I mean, we don't know. We know means we know abstractly by we can transform the L2 of Rn. We have defined gamma of S on L2 of Rn. Okay. But from L2 of Rn, we can bring it through the unitary here. But we don't have a direct definition on this. We know only its existence. Okay. So here it's defined directly. I mean, so yeah, it satisfies these two properties. You want to say something? I forgot. By this, we can precisely say what is gamma of S. Okay. Or we don't, I don't know whether I require this theorem later. I mean, later he computes all the pure state. Maybe it's required there. I don't know. Okay, let me see whether to prove it or not. Okay, I mean, I'll think about it tomorrow. But otherwise, we have to see this gamma S is used frequently everywhere. Okay, and he says it is determined up to alpha. So it's not used in a well-defined manner. Okay, so unless we have this, it is not clear. I don't know. I mean, we have to know what is gamma of S, right? We know gamma of S only through that property. Okay. So we have to know what is gamma of S when we use it, right? This is explicitly we have one definition. Okay, right. That satisfies that. So we know that satisfies that. So I mean, it will be also be true that gamma of S1, S2 will be gamma of S1 times gamma of S2. So if you want to use that, it also satisfies the following property. Gamma of S1, S2 equal to, that's what I said, it's a homomorphism, right? So, gamma of S1 times gamma of S2. It's also true that gamma of S1 inverse is gamma of S1 star. I mean, it's also inverse here, it's unitary, okay? It also satisfies all this property. Okay, anyway, we'll see tomorrow. Day after tomorrow.